So how do you find the domain of a function? Well, the domain is usually best thought of in reverse by asking the question, what values of x can I not plug in to my equation? Well, when we have a line, little y equals mx plus b, you can plug anything and everything in for x. You can plug in negatives, positives, 0, fractions, decimals. It doesn't make any difference. And what we're going to try to show here is that that is exemplified on a graph where this graph goes on forever, obviously. And that means that every single x value is being represented as we walk down the number line and this graph goes on forever. Every x on the number line is being accounted for. Now again, asking ourselves that same question, what can I not plug in for x? So here's an expression where we've got ourselves a problem. We're not allowed to divide by 0. That is an undefined quantity. So therefore, if x were equal to -3, we would get x minus 4 divided by 0. That is undefined, and so x could be anything except -3. So in reality, as we think about this backwards in our mind, x cannot be -3. But it could be anything else, fractions, decimals, 0, positives, negatives, etc. So we write the domain in interval notation by saying x could be anything from -infinity up to -3, and from -3 to infinity. But notice that the parentheses are excluding the -3. And let's take a look at the graph. Well, this is an asymptote, and you saw asymptotes in Algebra 2 when you studied hyperbolas. And so most of the time when we draw these, of course this was made with technology, but most of the time we draw asymptotes as dotted lines. And so there's an asymptote there, and so this graph is suggesting that it goes on forever. That means all the x values are being accounted for. This goes on forever, except for, I've got a little break in the action here as soon as I get to -3. Let's take a look at another one. Same thing, we've got ourselves a denominator, and so when we have a denominator we need to worry. We need to worry about getting 0 in that denominator. And so you could just kind of sit here and reason it out. Like this one was pretty easy. We could just kind of take a look at it and say, okay, x can't be -3 because if x is -3, I get 0. But what about a more complicated expression? What can't x be now? Well, probably the obvious one is that x can't be 0 itself because 0 squared minus 0 is still 0. And probably the other obvious one maybe is +1. But what about -1? Could x be equal to -1? Would that work or not work? Well, the point I'm trying to make is that this trial and error business, it takes way too long. And so what you can do is you can algebraically set this denominator equal to 0, do whatever's necessary. In this case, factoring is the necessary skill that allows us to get our two answers. And it turns out that the only two that make that denominator 0 are 1 or 0. And so the interval notation would look like this: -infinity to 0, 0 to 1, and 1 to infinity. That's the interval notation for that domain. And if we take a look at the graph, we see the same thing. We've got ourselves some asymptotes. There's an asymptote here at 1, and there's an asymptote here at 0. Everything else is infinite, keeps on going. So all the values of x in between 0 and 1 are accounted for. All the values less than 0 are accounted for, and all the values that are bigger than 1 are also accounted for. What about a square root? Well, you can take the square root of 0. That works. But what you can't do is you can't take the square root of negative numbers, not in the real number system. And so we need to worry about values of x creating a negative outcome. So you could probably see that x cannot be, let's say, 2. Because that would make 4 minus 6 if x were 2, and 4 minus 6, of course, is a negative number. But again, we need some methodology so we can get all of the answers. So we just think about this in terms of what has to be true. And 4 minus 3x has to be greater than or equal to, you can have 0 underneath of a radical, equal to 0. And so if we solve this, x is less than or equal to 4 over 3. So that says all the numbers from 4/3 on down will work. And if you examine this closely, that means a bunch of negative numbers are working. So let's test one. Let's say x were negative 2. Got to write this correctly. Let's say x were negative 2. Well, that's going to create a positive number right there. So that would be 4 plus 6, which is the square root of 10. That's legal. So what we have here, all numbers less than or equal to 4/3. So the interval notation would look like this. And this time we use a bracket because 4/3 is included in this solution set. And if we take a look at a graph, this graph is much simpler to look at. And this graph, we can see that it starts at 1 1/3, or 4/3. So there are no values this way that are represented, but all the values all the way down here are all represented with this infinite graph. So let's generalize the idea of finding restricted domains. If you have a denominator, you need to worry about 0 in the denominator. If you have a radical, you need to set up an inequality greater than or equal to 0 because you need positive values underneath of that radical. And the key here is the even index. You can actually take the cube root of negative numbers. We don't need to worry about cube roots and fifth roots, but we do need to worry about the even roots. Now let's finish up with some notation that may or may not be familiar with to you. So the sum of two functions can be written as f plus g of x, which is equivalent to saying add the two functions together. F minus g of x says take the two functions and subtract them. F times g of x says take the two functions, multiply them, and so on and so forth. And of course, what we've been talking about is domain restrictions. If you're going to divide two functions, you better be certain that one of the functions is not 0. So let's take a look at two examples, and let's look at two different functions, f and g, and let's do two things with them. Let's add them together, and let's divide them, and we're going to determine the domain of each answer. All right, so let's take a look at choice A. So first, before we even add these two together, let's take a look at the domain restrictions. I know that x cannot be negative 2, that comes from there, and I know that x cannot be negative 1, that comes from the second fraction. Okay, so we've got that so far. Let's actually add these two together. We need a common denominator, so this needs an x plus 2, top and bottom, and common denominator over here, we need an x plus 1 over here. And so what we get is a numerator of x plus 1 plus x plus 2 all over the common denominator, x plus 1, x plus 2, which is going to give us 2x plus 3 all over the common denominator, x plus 1, x plus 2. And so hopefully you see that our final answer, the sum of these two functions, carries with it the same domain restrictions as we saw with the individual functions. X still cannot be negative 1 or negative 2. Those are the two values in the denominator that would make that denominator 0. In interval notation, it would look like this. And let's take a look at the example of division. So once again, we have x cannot be negative 2, x cannot be negative 1. Now when we divide, all we really have to do is flip and multiply. So this is 1 over x plus 2 times x plus 1 over x, which gives us a grand total of x plus 1 over xx plus 2. That's our finalized answer. And notice that the domain restriction doesn't quite match. It doesn't quite match. So it still carries with it the original domain restrictions. X still cannot be -2 or -1 because the original function had that domain restriction, and now there's an additional restriction of x because the division or the product of these two functions, the product of the reciprocal, is going to introduce a new domain restriction of 0. So the interval would look like this, -2, and to infinity. All right, two last examples. Let's get back to what we were talking about before about inputs and outputs. So this says if -1 is an input and 12 is the output, what is the value of B? Well, this is just a little math problem here that says my output is 12. Whenever I evaluate or input -1 for x. And you see what I have here is just an equation that has a single variable of capital B. So we have 7 plus B equals 12, and therefore B equals 5. Inputs and outputs. And finally, let's write a function based on a formula that we're familiar with. So we want the area of an isosceles right triangle. The length of the hypotenuse is x. So these are 45s. So if the length of the hypotenuse is x, that means each side must be x divided by the square root of 2. So a side of this triangle is going to be the square root of 2x over 2, if I rationalize that. Now area of a triangle is 1/2 base times height. And it just so happens in this example, the base and the height are the same thing. We'll call that the base, we'll call this the height, they're the exact same thing. So A of x is 1/2 square root of 2 divided by 2x times another square root of 2 divided by 2x. And we will get some canceling here. Together, these two make 2, so that's gone, and that leaves me with x squared over 4 for my area.